Welcome back, listeners, to the Neural Intel podcast. Let's dive into today's topic. We are plunging into a challenge that is, well, front and center in the world of large vision language models, or LVLMs. How do we make these, increasingly capable models better at complex, multi-step reasoning, the kind of slow thinking that involves careful deliberation? And critically, how do we do that without incurring these, frankly, exorbitant computational costs? As always, we'll focus purely on the technical details and the performance implications of the technology we discuss. We'll be sticking strictly to the technical mechanics, avoiding ethical considerations or inclusivity to keep our lens sharp on the engineering and the results.
That really is the core technical hurdle, isn't it? Imparting these advanced reasoning capabilities, particularly this slow-thinking visual reasoning, to the really massive models. It just becomes computationally prohibitive with the methods we've traditionally used. Techniques like reinforcement fine-tuning or RFT, they've shown promise, definitely, but mostly on smaller models. They just don't scale easily to the 30, 70, maybe even 100 plus billion parameter models we're starting to see. The cost is just immense.
Right, that computational wall. And that's exactly what the source material for this deep dive takes head on. We're unpacking a technical paper titled ProxyThinker, Test Time Guidance Through Small Visual Reasoners. And it introduces what sounds like a genuinely innovative approach, designed specifically to sort of bypass that huge training cost by doing something clever at inference time.
Exactly. Our mission here today is to meticulously unpack the technical nuts and bolts of ProxyThinker. We want to understand precisely how it operates, mechanistically, explore its specific performance implications across a whole range of different reasoning tasks, and, critically, assess the efficiency benefits it claims. We'll be sticking strictly to the technical analysis in the paper, so you, the listener, get a really clear picture of this technique's potential within the current technical landscape. And of course, to stay updated on the latest AI and ML research papers, including the one we're talking about today, do visit our webpage. The link is in the bio.
Okay, so the core idea here sounds quite elegant, actually. It really gets at what might be possible beyond just, training bigger and bigger models forever. It's essentially about transferring the smarts, or maybe more accurately, the sophisticated reasoning patterns from a small, highly trained model to a much larger, untrained one, and doing that without ever having to run that expensive training process on the big guy itself. It just works during inference when the model's generating its response. Okay, let's unpack this. So maybe let's set the stage properly by diving into the specific challenge this paper tackles. That high cost of training these slow-thinking models, especially in the vision language domain. We've all seen models that are incredibly fast, right? Direct answers, almost instant, like the fast-thinking mode you might associate with, say, GPT-4o. But there's this other class of models, the ones often called slow-thinking. They're designed to deliberate, to break problems down, construct multi-step reasoning processes.
That's right. And the source paper actually mentions examples like OpenAI O1, DeepSeek R1, QWQ, primarily in the language model space, models that show this kind of deliberative behavior. They're not just spitting out the most probable answers straight away. They're trained to generate intermediate steps, maybe reflect on their own thinking, potentially even self-correct along the way. And that approach has shown, well, remarkable success in tackling complex, multi-step challenges, particularly in areas like math problem solving, scientific reasoning.
And we're seeing this extended now to multimodal tasks, right? Allowing these large vision language models, LVLMs, to apply these structured reasoning processes to problems that involve images. So they can analyze visual data, understand spatial stuff, interpret diagrams, do calculations or logic based on what they see, building up to an answer through, hopefully, a transparent series of steps.
Exactly. Now, the technical method that's proven quite effective for developing these kinds of, let's say, verifiable step-by-step reasoning capabilities in LVLMs is reinforcement learning with verifiable rewards, RLVR. It's a type of reinforcement fine-tuning, RFT. The goal with RLVR is basically to train the model to generate reasoning paths where each step ideally can be checked for correctness, which leads to a final answer that's hopefully verifiable. It's a powerful paradigm, definitely, for enhancing trustworthiness and accuracy in complex reasoning.
Okay, powerful. But you mentioned it's also incredibly computationally demanding. Why is that, technically speaking? What makes RFT so expensive?
Well, there are primarily two major technical factors driving up the cost of RFT methods like RLVR, especially for large models. First, it's the memory requirement. Algorithms commonly used like proximal policy optimization, PPO, or group relative policy optimization, GRPO, both mentioned in the paper, they typically require keeping multiple copies of the model's parameters or related things like value networks or old policies, all in memory at the same time during training.
Whoa, okay. So if your model is, say, 7 billion parameters, You might need enough GPU memory to hold the equivalent of 2, 3, maybe even more copies of that entire 7B model just to run the training algorithm.
Precisely. And when you scale that up to very large models, 30 billion, 70 billion parameters, that memory footprint becomes enormous. It demands access to vast amounts of high bandwidth memory, usually expensive GPU memory. Even with top-tier hardware, that constraint alone can really limit the size of models you can feasibly train with these RST methods.
Okay, so needing multiple copies of the weights, that's one big hardware constraint. What's the second factor making RFT training so resource hungry?
The second factor is the complexity and the sequential nature of the training process itself. RFT typically involves this alternating cycle between two distinct phases. You've got a rollout phase where the model generates responses or reasoning paths based on its current policy. It's interacting, generating data.
Yeah.
Then there's an optimization phase where the model's policy gets updated based on the rewards or feedback it got during the rollout.
Ah, okay. So it's not like standard supervised fine-tuning, which is more like a straight feed-forward pass and then backpropagation. This sounds more intricate, like a dance between generating and learning from that generation.
Exactly. This back and forth, this rollout optimization cycle adds significant complexity to the training loop. It often needs careful synchronization, especially across multiple GPUs if you're doing distributed training. And it can involve complex calculations for things like policy gradient estimation or value function updates. This complexity, combined with needing many, many cycles to actually converge and stabilize, significantly stretches out the overall training time and the computational resources needed compared to simpler fine-tuning approaches.
And because of this double whammy, the memory demands and the complex, slow training dynamics, the paper points out this critical limitation. RFT methods are rarely applied to large VLMs, much beyond, 7 billion parameters? The computational wall just gets too high.
That's the bottleneck they identify. Scaling these sophisticated reasoning capabilities, especially the ones learned via RFT that encourage specific structured ways of thinking, to truly large models like 32B or 72B parameters, it becomes practically infeasible for many researchers or even industry labs. The compute needed for that RFT process is just too great.
Which brings us right back to you, the listener, and why this cost issue is so important from a technical innovation standpoint. If building these highly capable, reasoning-focused LVLMs requires this kind of prohibitive compute investment for training, it severely limits who can actually develop, improve, and deploy them. It restricts accessibility, slows down progress on robust reasoning in our biggest, most powerful models, and this is the exact technical barrier ProxyThinker is designed to sort of leap over.
Precisely. It offers a potential pathway to get those RFT-like reasoning benefits on the big models, but without having to pay that massive training toll. So let's get into the core technical insight, the idea behind ProxyThinker. A key observation highlighted in the paper, and really the technical motivation here, comes from this growing evidence. It suggests that RFT, especially when used for reasoning tasks, might not be teaching the model fundamentally new knowledge or core reasoning principles from scratch. Instead, it seems like it primarily elicits and amplifies reasoning behaviors and patterns that are already latent, meaning they kind of exist in a potential or probabilistic form within the base model's pre-trained distributions.
Huh. That's a really interesting technical perspective. So it's less about fundamentally reprogramming the model's brain and more about finding a way to unlock or just prioritize existing pathways that relate to structured thinking.
That's a pretty good analogy. Think of the base model like it's learned this vast landscape of connections between words and concepts. Within that landscape, there are paths that lead to quick, direct answers. But there are also other paths, maybe less probable initially, that correspond to more roundabout step-by-step deliberation. RFT, through its reward mechanism, effectively shifts the probability mass within the model's output distribution. It makes those tokens and sequences that represent structured, slow-thinking strategies, things like, let's break this down, or wait a minute, or however, or is that actually right? It makes those much more likely to be generated. These strategies were probably implicitly there in the massive pre-training data, and RFT just makes the model favor them explicitly during generation.
Okay, that makes sense. So if the potential for this kind of structured thinking is already baked in, just maybe hidden under a preference for faster outputs, how does ProxyThinker technically leverage this at inference time, after all the training is done, to bring that potential out in a large model?
So ProxyThinker is presented as a technically simple, but seemingly quite effective method that operates entirely at inference time. Or test time, same thing. This means absolutely no further training updates are needed for the large base model we want to improve. It works during the forward pass, as the model is generating its response. The central idea is to transfer these desirable visual reasoning capabilities, those slow thinking patterns learned via RFT, without any of the associated training costs for the large model itself.
Okay, just to be crystal clear, the large model we're trying to make smarter with this method, it doesn't undergo any RFT training at all using ProxyThinker.
Correct. Its parameters stay fixed, frozen. The concept, which they visualize nicely in Figure 1 of the paper, shows a small, specialized reasoning model, essentially acting as a guide for the generation process of a much larger model. You can think of it as a form of dynamic knowledge distillation, or maybe behavioral transfer, happening on the fly during decoding.
Right, okay. Here's where it gets really interesting for me. How does this guidance actually work technically? How can a small model influence the complex decoding process of a much larger one in real time without changing its internal weights?
The core mechanism relies on comparing the output probability distributions, specifically the raw logit vectors of different models at each step of the decoding process. ProxyThinker uses the difference between the last token logits computed by two smaller auxiliary models. One is a small model that has gone through RFT training, ideally using verifiable rewards. This is the reasoning expert model, which they call BR1. The other is a small model that hasn't received the specific RFT training. It's essentially just the small base model version. This is the amateur model called P-101, P-0. Both P-101 are smaller versions, like maybe the 7B parameter versions, of the large model, capital Psi, that we actually want to guide, which might be 32B or 72B.
Ah, okay. So you take the raw output scores, the logits, for every possible next word or token. And the difference in those scores between the RFT-trained small model, the expert, and the standard small model, the amateur, that difference somehow captures the specific RFT-ness or the structured reasoning preference learned through RFT.
Precisely. That logit difference vector, mathematically is a SAM-Jello, captures the relative preference the small RFT expert has for certain next tokens compared to the small amateur model. It highlights the tokens that the RFT process made significantly more likely, or perhaps less likely, in the expert's output distribution at that specific point in the generation. This difference sort of embodies those subtle probabilistic shifts that correspond to initiating or continuing a structured reasoning process. ProxyThinker then takes this logit difference vector, scales it by a factor, and adds it directly to the logit vector produced by the larger base model.
I see. So the large model computes its usual probabilities for the next token, but just before it picks one, ProxyThinker gives those probabilities a nudge, a bias, based on the signal derived from the difference between the two small models.
Exactly. The core formula, equation 1 in the paper, lays it out clearly. P softmax Zex XEI plus AEECO. XEI, let's break that down. KC are the logits from the large base model. The term Zex ECI is that crucial logit difference between the small expert 1 and the small amateur process CO. This difference is scaled by a hyperparameter, a alpha, which controls how strong this steering signal is. This scaled difference vector gets added to the large model's original logit, say. This effectively boosts the scores, logits, of tokens that the RFT expert favors more than the amateur, and potentially suppresses tokens it disfavors. Finally, the softmax function turns these adjusted logits into the final probability distribution path from which the next token test is actually sampled.
Okay, so the formula is basically taking the large model's raw prediction tendency and tweaking it based on the RFT learned bias that we see when comparing the small expert to the small amateur. Tokens that signal things like think more, break it down, check your work. The stuff the RFT expert learned to favor, probabilistically they get a positive boost in the large model's decision-making for the next token.
That's precisely the mechanism, and it's a continuous adjustment happening at every single token generation step. Once the next token is sampled from this steered distribution path, that token gets added to the sequence X. Then the whole process repeats for the next step. All three models, the large bases, the small amateur SOAR, and the small expert 1, process the new longer text prefix along with the input images, calculate their logits for the next potential token, and that logit difference steering gets applied again.
Wow, so it's a dynamic autoregressive loop where the small expert's differential thinking continuously guides the large model's step-by-step generation process. It's not teaching the big model new facts, like you said, but it's subtly influencing its decoding path to follow a more structured, more deliberative route specifically. The kind of route that the expensive RFT process instilled in the small expert. That different signal is really the key.
That logit difference vector acts as the carrier, the signal, for that RFT learned behavior.
All right, this is making sense. Let's move from the formulas and the intuition to see this in action. The paper includes some case studies, right? Figure 2 looks like a good example from the MathVision data set. It's a geometry problem about the area of an L-shaped room from an image.
Yes, that case study in Figure 2 is very illustrative, particularly in showing how ProxyThinker leverages the large model's capacity. The problem is about calculating area, and the prompt given to the models includes an initial reasoning step that actually contains an error. Something about double counting or missing shared boundaries when breaking the shape down mentally. Now, when the large base model and the small base model are given the same flawed starting point, their default behavior, as shown in the figure, is often just to proceed directly. They finalize an answer based on that incorrect premise without much critical evaluation.
So they just follow the flawed reasoning provided in the prompt, kind of blindly. Essentially, yes. Their standard decoding process doesn't seem to have strong built-in self-correction signals for this kind of thing. Now, contrast that with the small RFT expert model in the figure. Given the same incorrect prompt, it shows these characteristic self-verification or pausing behaviors, things that were likely reinforced during its RFT training. You can see it generating tokens or sequences that indicate hesitation or checking. It might assign higher probability towards like, wait, however, but, or maybe try to initiate a different line of thought.
Okay, so the small expert has learned the behavior of pausing and questioning when something might seem off. But does it actually have the capacity, being a smaller model, to consistently fix a complex math error like that on its own? Well, the paper's analysis and the specific example in Figure 2 suggests that while the small expert definitely acquires the behavior of pausing and checking, its overall capacity and knowledge are still limited compared to a much larger model. In this example, the figure indicates the small expert's attempt at self-correction might be a bit shallow. Maybe it just restates parts of the problem or doesn't fully diagnose the root cause of the error. The small expert itself might still end up with the wrong answer or just get stuck.
But here's where ProxyThinker comes in, right? What happens when that specific RFT-induced logic difference signal that, hang on, something might be wrong here, signal from the small expert is applied to steer the decoding of the large base model?
That's where you see the synergy. ProxyThinker, by applying that scaled logit difference for virtual to the large base model's logits, successfully transfers this crucial reasoning behavior. The guided large model starts generating those same kinds of deliberative tokens, wait, however, but, and this is crucial, because it's the large model that is now exhibiting this behavior, it can leverage its significantly greater capacity, its deeper understanding of geometry, arithmetic, whatever the domain requires to perform effective self-correction.
Ah, I get it. It gets the trigger, the nudge, to pause and reevaluate from the small expert's signal, but then its own larger, more capable brain kicks in to actually figure out what's wrong and fix the reasoning. So in that MathVision example, where the prompt might lead to a naive calculation like 4 times 4 equals 16, missing the shared sides, the ProxyThinker guided large model picks up the self-correction cue, and it correctly identifies that, oh, shared sides need to be handled differently, maybe subtracted. It performs the correct steps, shown in the figure leading to an area of 10, and gets the right answer for the L shape.
Exactly. It's the structured behavior pattern from the small expert unlocking and directing the latent, higher capacity reasoning abilities that were already present, just maybe dormant, in the large model.
Okay, let's look at another one. Figure 6 you mentioned. That's a common sense spatial reasoning problem. How many people can sit at 4 square tables pushed together in a row, assuming each table normally seats 4?
Yeah, this is another great example showing the transfer of reasoning process and structure. The simple, often incorrect answer, as shown by the large base model in the figure, is just naive multiplication. 4 tables times 4 seats per table equals 16 seats. The base model just outputs this, with no real reasoning path shown.
Straight to the wrong answer. What about the small RFT expert?
The small expert, as depicted in the figure, demonstrates that its RFT training instilled this pattern of initiating a more deliberate thought process. It often uses explicit tags, like think, to mark its internal steps. Within these tags, it attempts to reason through the problem. Now, it's worth noting, as the paper does, the specific calculation shown in the text of the Figure 6 example seems a bit inconsistent internally. It shows something like 16 total sides minus 3 shared sides equals 13. But the final answer box shows 10, and 10 is the correct answer for 4 square tables pushed end to end in a line.
Okay, so maybe a slight typo or inconsistency in the numbers within the figure's text explanation, but the core point is about the process it tries to follow.
Exactly. The crucial takeaway illustrated by the figure isn't necessarily numerical perfection of the small expert's attempt, but the transfer of the style and structure of thinking. The small expert learned, through RFT, to initiate a structured process, maybe using think tags, breaking down the problem visually or conceptually.
And how does ProxyThinker use that process signal from the small expert to guide the big model?
ProxyThinker applies that small expert's logic difference signal to the large base model. The result, shown in the middle panel of Figure 6, is a much higher quality, step-by-step reasoning process generated by the large model. It adopts the structured format, maybe using think tags that the expert did, and proceeds to generate a much more interpretable chain of thought. It correctly identifies the concept. Pushing the tables together forms one long rectangular table. It understands that the shared sides become unusable for seating. The guided large model produces a reasoning path that correctly identifies the initial potential capacity, 16 side seats, and then reasons about subtracting or recalculating based on the shared sides. It understands there are 3 inner shared sides, each eliminating 2 potential seats. Or visually, it sees a long table with 4 seats on each long side, 8 total, plus 1 seat on each end, 2 total, giving 10 seats. So again, focusing on the process transfer, the guided model generates a structured, deliberative path. It's significantly more likely to arrive at the correct answer through understandable steps compared to the base model's direct, incorrect guess.
That clarifies it beautifully. It's less about the small expert being a perfect reasoner itself, and more about it having learned the meta skill of structured, careful thinking through RFT. ProxyThinker then sort of implants that meta skill pattern into the large model's decoding, allowing the large model to use its superior capacity to actually execute the reasoning steps correctly. The small expert provides the how to think template, and the large model provides the what to think about power.
It's a really powerful technical demonstration, isn't it? Showing how these behavioral patterns, not just static knowledge, can be transferred and leveraged dynamically at inference time using this logic steering technique.
Seeing that behavioral transfer in the qualitative examples is definitely compelling. But does it actually translate into better performance on a larger scale across different kinds of tasks? Let's pivot to the quantitative results in the paper. What benchmarks did they use to really test ProxyThinker?
Right. For the quantitative assessment, they used a pretty comprehensive suite of benchmarks. They included CV Bench, which really focuses on fundamental vision-centric tasks, things requiring spatial reasoning, counting objects, estimating depth, judging distances from images. Then, for visual reasoning challenges that specifically involve mathematical concepts, they used established benchmarks like MathVista, MathVerse, and MathVision. And to evaluate performance on broader, multidisciplinary questions, the kind that need understanding of images and text across various domains, they used MMMU and also R11 Vision Bench. The main evaluation metric for most of these was typically pass at 1 accuracy. Basically, did the model get the correct answer on its first try?
Okay, a good mix of tasks. What were the key findings when they applied ProxyThinker across these? Let's maybe start with the vision-centric results. I think that was table 1.
Yes. Table 1 focuses on vision-centric reasoning. They used a Qwen2 VL7B model as the large base model, guided by smaller 2 billion parameter experts, and they specifically compared using a small expert trained with standard supervised fine-tuning, SFT, against one trained with RFT, specifically using GRPO. The results there were pretty clear about the benefit of the RFT signal. ProxyThinker, applied to the 7B base model but guided by the RFT expert, the Qwen2 VL2B GRPO1, achieved a significant overall performance boost of plus 3.6% on the challenging CV bench compared to the 7B base model running alone.
Wow, okay, a 3.6% absolute jump just from an inference-time steering method on a benchmark like CV Bench. That's quite notable. That's not a trivial gain at all.
No, it's not. And the improvements were even more pronounced on specific subtasks within CV Bench. They saw gains of plus 7.9% on depth estimation and plus 6.8% on distance judgment. This suggests that the RFT signal from the small expert was particularly good at steering the larger model toward the specific reasoning patterns needed for those kinds of spatial tasks. And importantly, using the SFT-trained 2B expert, Qwen2 VL2B SFT with ProxyThinker, it did not produce similar gains. In fact, it resulted in a slight overall decrease, mega 0.2%. So this provides strong quantitative evidence that it's the specific reasoning behaviors learned through RFT, not just general fine-tuning, that provide the valuable steering signal for ProxyThinker.
Okay, that makes sense. The RFT secret sauce in the small expert is crucial, especially for tasks needing careful spatial or geometric reasoning. How did ProxyThinker fare on the more complex mathematical and multidisciplinary benchmarks? That was table 2, right? Using even larger 32B and 72B base models.
Yes. Table 2 extends the evaluation to show ProxyThinker's effectiveness with these much larger base models, specifically Qwen 2.5 VL32B and 72B instruct models. And they use different 7 billion parameter RFT experts as guides models like OpenVLThinker 7B, ThinkLite VL7B, and VLRethinker 7B. The quantitative findings here are really consistent and quite compelling. ProxyThinker led to performance improvements across almost all the mathematical and multidisciplinary benchmarks they tested: MathVista, MathVerse, MathVision, and R11 Vision Bench.
So it seems to consistently enhance reasoning performance across different types of complex tasks, and it scales up effectively even when the base model is very large.
That's what the data suggests, and there are some particularly striking results within Table 2 that are worth highlighting. For instance, using the OpenVLThinker 7B expert to guide the Qwen 2.5 VL32B instruct model. ProxyThinker boosted the accuracy on the MathVision test set from a baseline of 38.4% all the way up to 40.8%.
Okay, wait, let's pause on that. 40.8%. That's significant because, as the picker points out, that score surpasses the performance of a 32B model that was directly trained with the full, expensive RFT process, the VLRethinker 32B model, which scored 40.5% on that same MathVision benchmark.
That's the really eye-catching result from that comparison, yes. ProxyThinker, just using a small 7B expert to influence a 32B base model at inference time, achieved slightly better performance on MathVision than the same size 32B model that underwent the whole RFT training procedure. This really lends strong support to the paper's core hypothesis, that the reasoning potential is latent, and it can be effectively unlocked, maybe even more cleanly or effectively for certain tasks, using clever decoding strategies, rather than needing direct RFT training on the large model itself.
And the power of that finding is magnified when you remember how the small expert itself performed, right? The OpenVLThinker 7B expert that provided the steering signal only scored, 25.3% on MathVision. It's a decent 7B RFT model, but nowhere near the 32B model's performance level.
Exactly. That strongly reinforces the idea that ProxyThinker isn't just making the large model copy the small expert's answers. It's transferring the method, the pattern of reasoning that the expert learned via RFT. The large model then uses its superior capacity to execute that method much more effectively and arrive at the correct answer more often. It's like the small expert provides the reasoning structure or template, and the large model provides the knowledge and the computational horsepower to fill it in correctly.
The paper also mentioned, I think, that the quality of the small RFT expert matters.
Yes, they did show that using stronger RFT experts, for example, the VLRethinker 7B, generally performed better on its own than OpenVLThinker 7B, tends to result in slightly better ProxyThinker performance as well, which makes intuitive sense, right? A more capable RFT expert probably provides a cleaner, more effective signal for steering the large model's reasoning process.
Okay. Was there any type of task where ProxyThinker didn't seem to help much?
Yes, that's an interesting point. They found no significant gains on the MMMU benchmark. MMMU is known for being very knowledge-intensive. It tests a model's ability to answer questions requiring broad, multidisciplinary knowledge, often grounded in some visual context. On this benchmark, neither the small RFT experts themselves nor the ProxyThinker variants showed statistically significant improvements over the base models. This suggests that ProxyThinker's main benefit, and perhaps the benefit of the RFT training it leverages, is primarily focused on enhancing the structure and process of reasoning and problem solving. It seems less about injecting new factual knowledge or improving recall on purely knowledge-heavy tasks. It's more about how the model thinks through a problem, not necessarily what factual information it possesses.
Okay, so putting all this quantitative data together, what's the bottom line? It sounds like ProxyThinker offers a technically viable and often very effective way to get the benefits of sophisticated RFT-style reasoning on large models. And it can potentially match or even exceed the performance of a fully RFT-trained large model on certain reasoning tasks, all without paying that massive training cost for the large model itself. That feels like a significant technical step forward for efficiency and accessibility in deploying advanced reasoning.
It really makes a compelling case for unlocking latent potential through smart inference-time design, rather than always resorting to more brute force training. Okay, so let's dig a bit deeper into some of the analysis the paper provides. They look into things like robustness and practical efficiency. For instance, they investigated how sensitive ProxyThinker is to that hyperparameter, alpha.
Right, alpha. That's the scaling factor in the core formula, the one that decides how strongly the small expert's logic difference actually influences the large model's decoding process.
Correct. Figure 4 in the paper shows experiments where they swept different alpha values, testing on MathVerse and MathVision. The results suggest that ProxyThinker is relatively robust. You don't need to pinpoint one exact value. Alpha values typically between zero point 0.1 and 1.0 consistently gave performance improvements over the baseline model, which is effectively zero, no steering.
So you don't need to spend ages finding one single perfect, super sensitive alpha value for it to actually provide some benefit.
No, it seems the performance gains are fairly stable within that reasonable range. What's interesting, though, is that while the default alpha zero point 0.5 they used in the main tables works well, tuning alpha slightly can sometimes push the performance even higher. As Figure 4 shows, for certain expert models like VL-Rethinker 7b, carefully picking an alpha value allowed ProxyThinker to achieve performance on MathVision and MathVerse that actually matched or even slightly surpassed the performance of the full-scale RFT-trained 32B model, VL-Rethinker 32B. So it suggests there might still be some optimization potential just by tuning that one inference time parameter.
That's pretty impactful, isn't it? Tuning one knob at inference time could potentially get you performance equivalent to, or even better than, an incredibly expensive training run.
It really highlights the technical leverage of this kind of method. They also show, as you'd expect, that if alpha gets too large, the performance eventually degrades and starts to look more like the performance of the small expert model itself. Which makes sense if alpha is huge. The small expert's preferences are almost completely dominating the large model's own calculations, basically forcing the large model to just mimic the smaller, less capable one.
Right, you want guidance, not a complete takeover by a less powerful model. What about analyzing the nature of the reasoning improvement? The paper mentions pass-at-k analysis.
Yes. Figure 5 shows the pass-at-k results. Pass-at-k is a metric that tries to measure the probability of finding a correct solution within, say, k-generated attempts or samples. It's used to probe the model's underlying reasoning capacity, going beyond just its ability to produce the single best answer on the first try, which is pass-at-1, typically measured by greedy decoding. Now, some prior research on RFT has occasionally shown an interesting effect. While RFT significantly boosts pass-at-1, making the model much better at getting the right answer greedily, it can sometimes paradoxically reduce pass-at-k for higher values of k compared to the base model. The interpretation often given is that RFT might make the model very efficient at finding and sampling the single best reasoning path, but could potentially reduce the diversity or exploration of alternative valid reasoning paths.
So RFT might make the model like a laser-focused sharpshooter, but maybe narrow its overall field of view a bit?
That's one way to think about it, yeah. So Figure 5 first confirms this effect happens with smaller RFT models. Then they compare the 32B base model, the full RFT 32B model, VL-Rethinker 32DB, and their ProxyThinker 32B. What they find is that ProxyThinker 32B achieves the highest pass-at-1 accuracy, which confirms the greedy performance gains we saw back in Table 2. But for higher values of k, like KR2, ProxyThinker's pass-at-k curve consistently lies between the curve of the base model and the curve of the full RFT expert.
Okay, what does that intermediate position tell us?
It suggests that ProxyThinker might be striking a nice balance. It inherits the RFT expert's ability to efficiently sample high-quality reasoning paths that's reflected in its leading pass-at-1 score. However, because it's ultimately operating on the larger, potentially more diverse base model, it doesn't seem to suffer the same degree of reduction in exploration or diversity that the full RFT model shows when you look at multiple attempts, higher k. It seemed to retain more of the base model's inherent capacity for generating a variety of plausible reasoning paths, while still effectively biasing the top-ranked path towards the preferred RFT style. It's kind of the best of both worlds, efficiency plus underlying capacity.
Okay, performance looks good, robustness seems decent, but the initial motivation was all about cost. Running 3 models simultaneously, the big one plus 2 small ones for every single decoding step, sounds like it could be really computationally expensive at inference time, even if the training was free. How did they tackle the practical efficiency of actually running ProxyThinker?
That's an absolutely critical point, and they address it directly in their inference efficiency analysis, shown in Table 3 and illustrated conceptually back in Figure 3. The paper is quite upfront that a naive implementation where you just sequentially run the large model, then the 2 small models, get their logits, calculate the difference, adjust, sample, and repeat, yeah, that would be very slow. It's been a limitation of some previous decoding time steering methods. However, they put significant effort into developing a carefully optimized implementation specifically for ProxyThinker.
And what were the technical tricks they used? How did they make it fast enough to be practical?
Their optimized approach leans heavily on modern high-performance inference frameworks, specifically mentioning the VLLM framework, which is known for its efficiency features like page detention. The core idea, which Figure 3 tries to illustrate by showing minimized idle time, is all about parallel execution and smart resource utilization across multiple GPUs. For the large base model, which obviously dominates the computation and memory needs, they use tensor parallelism. This means splitting the model's layers or weights across several GPUs and computing different parts of the logic simultaneously. Then, for the smaller expert and amateur models, which are less demanding individually, they run them asynchronously in separate process groups, possibly on different GPUs or sharing GPUs efficiently.
Okay, so the small models are working away in parallel, and the big model is also being processed in parallel across different resources.
That's the idea. The logic computation for all three models is happening concurrently, or at least with heavily optimized overlap. The logics from the smaller models are then transferred efficiently, probably using fast interconnects and collective communication operations, to the process group handling the large model. That's where the logic difference is calculated and applied to the large model's logics just before sampling the next token. This whole carefully orchestrated dance minimizes idle time and keeps the GPUs busy.
And the results? What did this optimization actually achieve in terms of runtime speed?
The results they report in Table 3, benchmarked on a segment of the MathVision test set, are pretty dramatic. Their optimized ProxyThinker implementation achieved a speedup of up to 38 times, that's 38, compared to a naive implementation using standard libraries like Hugging Face transformers.
Wow, 38x faster. That's easily the difference between a technique being theoretically interesting but practically unusable in many applications versus something that's actually viable for deployment.
It absolutely is. And crucially, they benchmarked this optimized ProxyThinker setup against running a single full-scale RFT32B expert model, the VL Rethinker 32B, using the same efficient VLLM framework on the same hardware configuration. And the measured runtime duration for their optimized ProxyThinker setup, large base plus 2 small guides, was very close to, in some cases even slightly faster than, running just the single 32B RFT expert model by itself.
Hold on. So you can potentially get the enhanced reasoning performance that might otherwise require training a full-scale RFT32B model, maybe even beating it in some cases, and you can do it at approximately the same inference cost as just running that single large RFT model.
That's the key technical implication they present. It means you're effectively getting the reasoning benefits associated with an expensive RFT process without paying the training cost. And the inference overhead of running the two smaller guidance models alongside the large one has been optimized down to be practically negligible, or at least comparable to running the large model alone. It makes acquiring these RFT-like reasoning capabilities much more accessible and potentially deployable for very large models.
Yeah, that technical efficiency piece really feels like a crucial contribution here. It moves ProxyThinker from just being a clever theoretical idea to being a potentially practical method people could actually use.
Definitely. It bridges that often wide gap between theoretical potential and real-world applicability. So just to wrap up by placing ProxyThinker in the broader technical context, it's useful to see how it relates to other research happening in the world of large vision language models and methods for controlling their behavior.
Sure. How does it build on or differ from other approaches we might have heard about?
Well, it certainly builds upon the huge advancements we've seen in the LVLMs themselves. It acknowledges their impressive general abilities, but also highlights that persistent challenge of getting them to do robust, multi-step reasoning that really needs deep integration of vision and language.
And as we've discussed quite a bit, it's directly motivated by that recent work using reinforcement fine-tuning, RFT, to improve visual reasoning. The paper cites specific prior models and frameworks, OpenVLThinker, ThinkLightVL, VLRethinker, various R1-style approaches.
Exactly. Those prior works really demonstrated that RFT can be effective for enhancing reasoning in VLMs, but they kept hitting that computational cost wall when trying to apply it to the really large models. ProxyThinker's main technical contribution, then, is providing this cost-effective alternative, a way to acquire those same RFT-like reasoning behaviors in the bigger models without needing to do the expensive RFT training directly on them. It cleverly leverages the outcome of RFT on a small model to benefit a large one just at inference time.
It also sounds like it shares some DNA with other methods that modify model output during decoding. These are sometimes called decoding time algorithms or test time techniques.
Yes, absolutely. It sits alongside that whole line of research exploring how you can influence or steer a model's output after it's already been trained. We've got methods like DEXperts, which use logic differences from expert and anti-expert models to steer general attributes like sentiment or toxicity, There's contrastive decoding, which contrasts outputs from a standard model with maybe a negative or simpler model to improve things like factuality or coherence. DOLA, decoding by layer attention, looked at comparing logits from different layers within the same model to try and reduce hallucinations. And VCD, visual contrastive decoding, uses visual information specifically to help steer text generation to be more grounded in the image.
Okay, so there are other techniques manipulating logits at decode time. How does ProxyThinker really differentiate itself from those?
While they all share the general idea of modifying the decoding process, often using logit manipulation, ProxyThinker has a very distinct technical goal. Its objective is specifically to transfer reasoning abilities that were learned via RFT. It's not just steering for general attributes like sentiment or overall factuality or broad visual consistency. It's using the logit difference derived from a specifically RFT-trained expert model to encourage the large model to adopt the structured, deliberative thinking patterns that RFT is known to reinforce. It's this targeted approach using the small RFT expert as the specific source of the steering signal to transfer a particular learned behavior that really sets it apart conceptually.
Right. That focus on transferring a specific training-induced behavior, the RFT reasoning style, using that targeted logit difference signal, rather than steering based on more static attributes or general contrasts. That seems like the key technical distinction.
Yes, precisely. It's tackling the challenge of acquiring a particular type of learned capability efficiently by leveraging the output dynamics of a specialized small model as a proxy guide. Okay, so to bring our deep dive into ProxyThinker, test time guidance through small visual reasoners to a close, let's quickly recap the core technical takeaways. ProxyThinker is presented as a simple, conceptually at least, yet demonstrably effective algorithm. Crucially, it's training-free and operates purely at inference time.
And its technical core is using that token-level logit difference, the difference between a small model trained with expensive RFT and a small base model, to actively steer the decoding process of a much larger base model. This steering mechanism probabilistically nudges the large model towards generating tokens characteristic of that slow-thinking, multi-step reasoning behavior, all without ever needing to change the large model's trained parameters.
And we saw through the quantitative results that this approach consistently enhances performance across a pretty diverse range of visual and multimodal reasoning benchmarks, including some quite complex mathematical tasks. Critically, it achieves these performance gains on very large models, 32 billion, even 72 billion parameters, thereby circumventing the need for that computationally prohibitive full-scale RFT training on those large models themselves. And those results on MathVision, where ProxyThinker actually surpassed a directly RFT-trained 32B model, were particularly noteworthy demonstrations of its potential power.
Yeah, and the practical feasibility is just as important as the raw performance numbers. The paper details those significant technical optimizations using modern inference frameworks like VLLM, tensor parallelism for the big model, asynchronous execution for the small ones, resulting in those dramatic speedups up to 30 times faster than a naive approach. This brings the actual inference runtime for ProxyThinker very close to, or even matching, the runtime of simply running a single large RFT expert model. That makes it a genuinely practical method for potential deployment.
Taken all together, the work provides pretty compelling evidence, I think, for the hypothesis that sophisticated reasoning capabilities might already be latent, already present, but maybe not easily accessed within large base models. And that maybe RFT primarily serves to make these capabilities more probable, more accessible during generation.
Yeah.
ProxyThinker then offers a highly efficient, purely inference-time mechanism to unlock and leverage that potential in larger models that would otherwise be too costly to train directly with RFT.
It really does feel like we're maybe just scratching the surface of what can be achieved purely at inference time with these massive models, doesn't it? If complex reasoning behaviors are indeed residing within these architectures, just waiting for the right kind of probabilistic nudge from a clever decoding strategy like this. Well, what other sophisticated capabilities might be waiting to be unlocked? Maybe through similar training-free techniques, perhaps guided by other kinds of specialized small models or different signals. That's a really fascinating technical question that this work certainly pushes to the forefront.
It definitely opens up some exciting avenues for future research into eliciting and controlling model behavior much more efficiently.
Absolutely. And for you, the listener, if you want to really dive into the specific equations, look closely at the figures, scrutinize the benchmark results, or get deeper into those technical implementation details, we highly recommend checking out the source paper itself. You can find the link to ProxyThinker, and as always, stay updated on other cutting-edge AI and ML research papers by visiting our webpage, which is linked there in the bio.
Thank you for joining us for this technical deep dive today.
Until next time on Neural Intel.